So welcome to video problem 11. Here we will use Ampere's law to determine the magnetic flux density, which is the B field, for a uniform steady line current in free space. This is our configuration. It's an infinite line current where the current is assumed positive, and it's residing in a free space host medium with free space permeability mu0. The objective is to determine the B field at this observation point that you can see here. We introduce two coordinate systems, a rectangular coordinate system and associated circular cylindrical coordinate system, so that the current is infinite along z direction, and also so that the observation point has these coordinates. We then assume or postulate that the B field at this observation point only has a phi component, and that this phi component is only a function of the radial distance from the z-axis. And we will have to argue for this. If we take first the coordinate dependence due to translational symmetry, which is implied in terms of infinite and uniform current along z, the B field can obviously not be a function of z coordinate. Now, if we consider, for instance, this circle here of radius r, and if you consider some observation points on this circle, due to cylindrical symmetry, all of these points will see the same current. And that's why the B field cannot be a function of phi coordinate either. So we conclude that the magnitude of the B field indeed only depends on the radial distance r. Let's now focus our attention on components. Assume an r component of the B field. If we have an r component of the B field at this point, we will also have it at that particular point, also here and also here. This will obviously create a flux of the B field through this cylindrical surface that you can see here. But that will be in conflict with our fundamental law, which states that the flux of the B field through any closed surface S is always equal to 0. Thus, we have to disregard the existence of any R component for this particular current configuration. Let's then turn our attention to Z component. Assume, for instance, this rectangular path that we can see here, and assume at some distance r that we have a z component which will be directed like shown here. A little further distance away from the current, we will still have this z component, but since the distance has increased, we expect that the magnitude of this z component has decreased, as indicated here. Now, if we look at the second fundamental law, it states that the circulation of the B field along any closed path C is equal to free space permeability times the total current flowing along this path. Obviously, with those two Z components here, there will be a circulation of the B field along this rectangular path over here. So the left-hand side will be different than 0. But obviously, there is no current flowing through this gray surface which is bounded by this path. So we have to assume that there is indeed no Z component of the B field. Thus, the field has only a phi component, and this phi component will only depend on the radial distance. That means that if we consider, for instance, this cylindrical path over here of a constant radius r, we can use Ampere's law, which is given here, which states that the circulation of the B field along this closed path C is equal to mu0 times the total current flowing through this path. So we then proceed here with the details of our integration contour, and also getting the right dl element, and also getting the enclosed current through the surface bounded by this path C. Here we can see the path C over here, and this is the surface which is bounded by this path. So the total current passing through the surface here is given by our current in the line current, or alternatively we say that this is the total current which is enclosed by the path. So we know what the total current is. Now we have to determine this dl element, which is the infinitesimal differential length element on the integration path, and this is indicated by this blue arrow over here. So the radius of the integration contour is r, the increment in phi is d phi, so obviously the length of our arc here is r times d phi, and everything is in phi direction, so our dl will be given by the expression here. So now we have all the ingredients to actually use Ampere's law to determine the B field due to this current configuration. This is what we do here. This is Ampere's law. This is the general form of the B field for this particular configuration, and this is our dl element. Now we plug everything in our expression. So the integral is along this path C, and that's an integral in phi from 0 to 2 pi. This is our B field, and this is our dl element. We have a phi unit vector, which is dotted with a phi unit vector. This is unity. This field is only dependent on r, so it's a constant in our integration in phi, so we can take it outside. So the integration is rather straightforward to perform and gives this result of 2 pi r times the B field is equal to mu naught times the total current flowing through the surface enclosed by the path C, and this is exactly the current I. You isolate the magnitude, and you finally write the expression for the B field, which is given by the result here. So this really concludes our task in this problem. This is the final result summarized, and as usual we have some tasks for you. We would like you to work out the SI unit of the B field that you can see in the expression here. We would also like you to verify the fundamental postulates on the differential form at points away from the current, and we would also like you to figure out which component in rectangular coordinate system will the B field have for phi equal to 90 degrees. Thank you very much for your attention.